Okay, so my name is Shawn McKee. I am the OSG area coordinator for networking. I'm reporting on behalf of an extended team, shown on this slide. Okay, so first question, why OSG networking? So as you probably heard mentioned a lot in previous talks, the network can be a critical component for doing our science. It is the glue that ties together the storage and compute resources that are distributed. And the real issue that you face is that if you have a network issue, it can significantly impact OSG scientists who are trying to get the research done. Even halting it for a long time in some cases, we've had historical examples which were significant delays in certain people's workflows. And when you say the network, you have to be a little careful because the network is actually a complex entity. There are various networks that have to interoperate in the typical case to get the user from the source to the destination. And this makes problems that happen in the network a very big challenge because you need to know exactly what the problem is and ideally where the problem is to get it solved quickly. Another part of this is that sometimes people blame the network. It's not the network, it's the end systems. So you have to be able to also quickly differentiate when there are problems on the ends compared to something really happening in the middle. So with OSG networking, we really focused on trying to make sure that we can identify network problems when they happen and hopefully localize them to the extent possible. And so I wanted to give a little bit of information about some recent work. So half of this talk is really going to be about some recent work that we've been doing to look at the measurements we're making and try to get some progress in localizing things. So I always like to show this diagram. This is the LHC1 network. This is actually just a subset of the world's many networks. And this is what we use for high energy physics. And this is how we have to communicate. And you can see the spaghetti here.
By the way, that's the reason why the telescope people ship tapes.
Credit goes to Bill Johnston, who continues to maintain this. And actually the link on his name takes you to a presentation that Bill has for how to interpret this diagram and all the symbols on it. So for OSG and networking, we've been working on networking for more than 10 years, and we've developed an extensive infrastructure and set of tools for network monitoring and network analysis. So we have over 230 globally distributed Sonar toolkits at the larger compute and storage sites. We've developed a framework to monitor, manage, and configure the toolkit centrally. And we actually support multiple virtual organizations testing requirements using this infrastructure. We have a network data pipeline that centrally gathers all of the data. We have OSG WLCG specific documentation that augments the very good documentation that Sonar provides. We have an alerting and alarming framework that we've recently developed, and I'll talk a little bit about that. It allows people to self-subscribe to alarms that they may be interested in. We also have an application to visualize and explore those network alarms. And finally, we have an analytics platform to explore all of the extensive data sets that we have. A lot of these I'm not going to go into. In my backup slides, I have pointers to recent presentations on some of these and related topics, because I did want to spend some more time actually looking at some of the data, but that'll come shortly. We are currently in the middle of a pipeline transition. So this OSG network pipeline actually is responsible for getting about 6 terabytes of network metrics and associated metadata per year from all of these Sonar nodes and other data systems that we have. We have a central collector. There's a message bus. The central collector reaches out to the Sonar nodes, puts the data on the bus. There's a separate part that then ingests the data from the bus and puts it into a central Elasticsearch. Now with release 5, which has been out now for a couple months, we have an opportunity now to go to a new model. So we're going to be transitioning from a pull model into a push model. And we'll basically have the toolkits directly writing into Elasticsearch via Logstash. This reduces the complexity and the number of components that we have to maintain. And it also significantly reduces the latency, which opens up some new use cases for us. So instead of a 15 to 20 minute latency between the measurement being made and it showing up, we can get it within seconds now in many cases. This is what the pipeline looks like. It's a transitional pipeline because we do have a component here, which is the collector that's still running. Meanwhile, we have this HTTP archiver that allows the toolkits to directly write. You can see there's a lot of components here. These are part of the infrastructure that manages, configures, and monitors things, and eventually gets data into Elasticsearches that we can actually look at the data with. We have this alerts and alarming service. This is one of the most requested things that we've had over the last few years. People want to know if there's a network issue that impacts me. And so can you tell me if you think there's a network problem that impacts me? So we have it at this website, shows a little bit about how it's actually architected. In addition, we've augmented this alerting and alarming service with something called PS Dash. This is a Plotly-based application that lets us actually go in and explore the alert that you get, so you can find out some more information about it. You have the gray box with the alerting and alarming service, and PS Dash connects to that through Elasticsearch, basically, and allows exploration of the data. I encourage you to visit the URL and see what's available there. Here's what I really want to show you, though. I want to show you a little bit of the complexity that we have to deal with when looking at these network metrics. So our first challenge is that we have tests that run that determine the path through the network, the layer 3 path, basically traceroute. Many of you are probably familiar with it. We run that approximately every 10 minutes between our sources and destinations. So we understand what is the path that's in effect at that point when we look. Separately, on a time scale of anywhere once for every 6 to 24 hours, we'll do a throughput test. And then we'll also run latency tests that are summarized every minute. So you have these different time scales, and you have to end up figuring out how do you combine them effectively? How do you make use of that topology information along with a measurement on the network? And so you can see it schematically here. What we've chosen to do is actually, I'm going to show you an example for throughput and traceroute. So we have these measurements. We measure throughput, the squares, and of course we have all these ongoing traceroute measurements. And what we've chosen to do is there's an ambiguity when you make a traceroute measurement before and after a throughput measurement, and they're different. Which path do you attribute the throughput measurement to? We say we don't know. We're going to put it on both of them because that probably doesn't bias things too badly, and I'll show you what that looks like. We're actually evaluating this. The other option is just to take the last measurement that you have. Okay, so here is a set of measurements. So going down the diagram are different throughput measurements, and the results are shown on the right. And you can see it's site 1 to site 2, various measurements, from site 3 to site 2, and so forth. All the different boxes represent routers on the path when the measurement was made. And you can see we've colored them just to make them easy to discriminate. If I want to take the set of all of these measurements, I have this first measurement at 1770 megabits, 430, and 2. And then I see which routers were active for each one. And I attribute the measured bandwidth to each router along the path. So each router is accumulating a vector of measurements. You can see it if you go this way. So the first one saw 3 different measurements, and there's 3 different bandwidths associated with it. We can then take that and look at each router in turn, and we can plot it along a line. And then we can look for things where we have relatively large bandwidth and then some degradation, right? You can see maybe something's changing in that router. So we look for a downtrend. We set a threshold at about 10% of the maximum and see when it falls below that for an extended period. That can trigger us to say, maybe something's going on here. So this is actually graphically displaying that. So this is a particular router. All the blue dots represent different throughput values that were associated with that router by looking at the trace route. And you can see as a function of time, something obviously happened. This router was definitely involved with some significant decrease in bandwidth, right? And so this is getting us to the point where we can now start to localize where bad things happening in the network may be actually occurring. Okay, so that was an example of some of the complexity that we're trying to deal with. We also have a lot of collaborations. They're all shown here. I'm not going to go through them all. One of the main drivers we have, of course, coming up is the WLCG data challenge that will be next year. And we have a number of areas where we're working on network-related items for that data challenge. One of the big things we want to do is make sure we get perf sonar upgraded, new hardware installed, so that by this fall, we can start ringing out all the networks in advance of the data challenge and make sure that we're starting clean. We have a number of work areas that the group is continuing to contribute to. This is quite a long list, but all of these things are important. Many of them are very relevant for the data challenge. One of the interesting things that we're trying to do with the working group that we have is see to what extent we can develop AI and machine learning based on the data that we have. And a big part of the work that we're doing is better understanding the topology and also annotating the data that we have. So we're reaching out to ARNI networks and things like FTS and Rusio to have them give us incidents that they've had, when the incident started, when it ended, which sites were involved. We can then use that data along with all the network data we have, and we can start to semi-annotate that data based on those incidents and use that in unsupervised machine learning with this semi-annotation. So that's ongoing effort. So to conclude, a bunch of people, a collaboration of OSG, WLCG, and various research projects have created an extensive, reliable infrastructure to monitor our networks via perf sonar. We've engaged with various groups and we're working on improving networking scientific research. We have to also continue to monitor and maintain the networks and the infrastructure that we've developed, tuning things up, developing new capabilities. And of course, we have a number of challenges remaining, including the really difficult meta challenge of improving the tools that we present to the users. So I will conclude there, acknowledge funding that we've had and our collaborators. And again, I did mention that there are other presentations and there are links at the end of the presentation if people want more information. So I will stop there. Thank you.